To start, let us revisit the concept of formation reaction, which you first encountered in general chemistry. We define the standard formation enthalpy of a substance, delta F H standard, as the standard reaction enthalpy for the formation of 1 mole of that substance from its elements in their standard reference state. So we would write the formation reaction for CO2 gas as 1 mole of carbon solid graphite plus 1 mole of O2 gas to yield 1 mole of CO2 gas. The formation enthalpy for CO2 gas is minus 393.51 kilojoules per mole of CO2 gas. The standard reference state of an element at temperature T is the most stable form and phase of that element at temperature T and at P standard. The rule for figuring out the standard reference state of substances that you should use is as follows. Elements are in their standard reference state when they are in their atomic standard state in the solid phase, except for hydrogen, it's H2 or molecular hydrogen gas. For nitrogen, it's N2 or molecular nitrogen gas. For oxygen, it is O2 or molecular oxygen gas. For fluorine, it is molecular fluorine gas, F2. For chlorine, it is molecular chlorine gas, Cl2. For bromine, it is molecular bromine liquid, Br2. For iodine, it is molecular iodine solid, I2. For mercury, it is atomic mercury liquid. For argon, krypton, and xenon, it is the atomic gaseous form of the noble element. And for carbon, it is the solid graphite form of carbon, not diamond. In the next 2 slides, we will review how we use the standard formation enthalpies to calculate a standard reaction enthalpy. To start with, let us consider again the combustion reaction for methane and use Hess's law to express this combustion reaction in terms of the formation reactions for reactants and products involved in the reaction. We see that the formation of 1 mole of methane requires 1 mole of carbon solid graphite and 2 moles of molecular hydrogen gas. O2 is already in the molecular oxygen gas form associated with its reference state. The formation of 1 mole of CO2 gas, as discussed above, requires the combination of 1 mole of carbon solid graphite and 1 mole of molecular oxygen gas. Finally, the formation of 2 moles of water liquid requires the combination of 2 moles of hydrogen gas and 1 mole of oxygen gas. Note the different directions for the arrows in reactants and products. On the product side, we use direct formation reactions, while on the reactant side, we use the reverse of formation reactions. This was done so we can go from reactants to products by an alternate route using elements in their reference state as the intermediate state for the process. Note also that we obviously have the same number of elements in their reference state on the product side and on the reactant side, namely 1 mole of carbon solid graphite, 2 moles of molecular oxygen gas, and 2 moles of molecular hydrogen gas. So looking at the direction of the arrows, we see that the transformation of reactants to elements in their reference state has an associated standard reaction enthalpy change of minus the formation enthalpy of methane gas, minus 2 times the formation enthalpy of oxygen gas. The transformation of elements in their standard reference state to products has an associated standard reaction enthalpy change equal to the standard formation enthalpy of carbon dioxide, plus 2 times the standard formation enthalpy of water liquid. In the previous slide, we essentially used Hess's law to write the reaction equation for the combustion of methane as the sum of two reaction equations. The first reaction consists in the reverse of the formation reactions of reactants, while the second reaction consists in the direct formation reactions of products. The enthalpy change for reaction 1 is minus the standard formation enthalpy for methane gas minus 2 times the standard formation enthalpy for molecular oxygen. The enthalpy change for reaction 2 is the standard formation enthalpy for carbon dioxide gas plus 2 times the formation enthalpy for water liquid. So delta RH standard for the combustion reaction of methane is equal to the sum of delta H1 plus delta H2, which we can rewrite as the formation enthalpy for CO2 gas plus 2 times the standard formation enthalpy for water liquid minus the formation enthalpy for methane minus 2 times the formation enthalpy for O2 gas. Note that the standard formation enthalpy for O2 gas is equal to 0 since oxygen in the molecular gas form is the reference state for oxygen. This equation can be easily generalized to any chemical reaction by stating that the standard reaction enthalpy change for a chemical reaction is equal to the sum of the standard formation enthalpy change of the products multiplied by their respective stoichiometric coefficients, nu, minus the sum of the standard formation enthalpies for the reactants multiplied by their respective stoichiometric coefficients, nu.